Entropy is a measure of how much disorder there is in the system. At a molecular level, this means that there are a lot of, or at an atomic level, I should say, it means there are a lot of different states that the electrons of an atom could be occupying. At a macro level, you can kind of take a guess at what would be more ordered. Like if I stack up some books, that's more ordered than books strewn about everywhere. You know? So my desk has as you've seen, has a fairly large amount of entropy. My bedroom used to have more, but then I got married, and so now my bedroom has less entropy. Yeah. Now, we've talked about the Carnot relationship in a reversible engine, where this QC over TC equals QH over TH. This is actually an amount of entropy, a change in entropy, and entropy is defined with S, is defined as a heat per temperature. So its units, as we can see, are joules per Kelvin. So the change in entropy of a system is equal to the heat over the temperature. It is a state function, so it doesn't matter how you get from point A to point B. All that matters is that you do get from point A to point B. And we can see for a positive Q, if heat flows into the system, then entropy increases. If heat flows out of the system, then entropy decreases. And because entropy is a state function, we can calculate entropy by using a reversible process, even if the process used is not actually reversible. And now with this definition of entropy, we're assuming that the temperature of the system is fixed. So if heat flows in, then there are going to be more allowed states, and things are going to get more disorderly. But if this is not a fixed temperature system, then it becomes a calculus problem, and this is not calculus-based physics. So we're going to assume that we have fixed temperature systems. Now, for a reversible heat engine, the change in entropy, well, for any heat engine, the change in entropy is going to be minus Q hot over temperature hot plus Q cold over temperature cold. Because the Q hot is negative because heat flowing into the system is defined as negative. So when we plug in a negative value here, it's going to come out positive. So the entropy of the system, is positive. Yeah, and then heat flowing out of the system is a positive quantity as well. For a reversible, if this is reversible, the Carnot relationship applies, and this is equal to 0. I'm sorry, this is not this is the entropy change of like the universe, the area outside. So the Q hot flows out of the universe and into the engine, and then Q cold goes out of the engine and back into the universe. So both of these are defined as positive numbers. Okay, but they come out to a total of 0 if the Carnot relationship holds. For any non-reversible engine, the change in entropy winds up being positive. The entropy of the universe is always increasing. So a change in entropy for a process is always greater than or equal to 0. Sometimes locally, the entropy of the universe can decrease. For example, if you've got a pile of books, or not a pile, but you've got books scattered around and you put them into a pile, well, the entropy of those books decreases. But you have done work, and in doing so, you're giving off heat into the environment, and so the overall entropy always increases, even when locally it may seem like it is decreasing. So let's say, for example, we have a hot reservoir at 576 Kelvin, and it transfers 1,050 joules of heat to a cold reservoir at 305 Kelvin. I'm going to find the entropy change of the universe. Now, this isn't a heat engine, but we can still use our equation here. The heat coming out of the hot reservoir is 1050, that same amount of heat is going into the cold reservoir, but they're at different temperatures. The hot reservoir is at 576, the cold reservoir is at 305. And so this, the change in entropy of the universe is that, which we can punch into our calculator. Entropy change of the universe comes out to 1.6197 whatever joules per Kelvin. That's pretty simple. And that entropy is always increasing. Now let's say we have a heat engine with those same temperatures, let's say a heat engine with those same temperatures does 455 joules of work, while 1050 joules flow out of the hot reservoir. Actually, that might not be possible. Is that possible? We'll find out. So then now we want to know what is the entropy change of the universe. Well, our Q hot is still 1050, our T hot is still 576, our Q cold. Now, if it does 1055 or 455 joules of work, then the difference between those is how much energy flows back into the hot or into the cold reservoir, and that's over 305 Kelvin. Now, I questioned before whether this was possible. Well, we'll figure out if it's possible. If this comes out to be a positive number, then we're okay. If this comes out to a negative number, that means that this is not a possible amount of work. It would be more efficient than the Carnot limit, which actually can't happen. But let's see, if we punch this into the calculator, minus 1050 over 576 plus 1050 minus 455 over 305, we get a change in entropy of the universe of 0.1279 joules per Kelvin. So I guess that is possible because we had a positive change in entropy. Right. So now, if we're just not considering a heat engine anymore, if we're just considering spontaneous flow of heat from hot to cold, then the Q for both of them is the same. And our Q hot was negative and our Q cold was positive. So we can say this: if energy is just spontaneously flowing from hot to cold, because the Q's are the same, right? And if we then multiply our whole equation through by a T cold, we get Q minus Q T cold over T hot, which is, if we factor out the Q, is 1 minus T cold over T hot, right? And this 1 minus T cold over T hot was the efficiency of our Carnot engine, and Q times efficiency is equal to work. So therefore, if we have an irreversible process, let's say T cold delta times delta S equals work. So this gives the increase in entropy of an irreversible process, and the work that would be done by the reversible process. Remember, for an increase in entropy, it doesn't matter what the process was. So this is an increase in entropy regardless, but this does give the work done by a reversible process direct relationship to entropy. Now, combining two things that we've already talked about. I mentioned that the change in entropy of the universe is always increasing, and that's because of the second law of thermodynamics, and that was that heat goes from hot to cold. And when that happens, the entropy of the universe increases, which in the very long term, scientists say will lead to the heat death of the universe. meaning that, stars are generating heat, and planets have some heat from, different, there's some heat in the core, energy coming out of the core that we're really not entirely sure where that's coming from at this point. But, there's energy that's moving around in the universe. But in the very, very long term, entropy is going to keep increasing, and heat is going to keep flowing from hot to cold, and everything will kind of even out in terms of temperature, and everything will go to the most disordered state possible. And really, collections of molecules and cells and life and whatnot is a low entropy state of affairs. We would have a lot more entropy if we were just a puddle of random particles on the floor. The average temperature of the universe is really just like, it's only a couple Kelvin. I think they think it's somewhere between just a couple of kelvins, 1 to 3 kelvins. And if everything kind of evens out, the hot heat of the stars leads off into space and so forth, then that will, in the very, very long term, lead to the heat death of the universe, where everything is just kind of cold and lifeless and not collected into particle, orderly groups of particles in the very long term. And I think that's, a good picture of how the universe would function without God, without some external intervention that is not a part of creation. Everything will eventually be cold and lifeless, and there really wouldn't be any long-term hope for anything. Yeah. Note that we've already mentioned, but I didn't state, as the third law of thermodynamics. I already mentioned it, but didn't state that it was the third law, and that is just that no object can reach a temperature of 0 Kelvin. That is the third law. Now, they have produced negative Kelvin temperatures at this point, but as far as I know, this law remains unviolated, that no one has produced a temperature of 0 Kelvin, the point where all molecular motion ceases.